In the previous section, we had determined the slope of this. Let's go ahead and use that to make our mathematical model. So we'll use the symbol t, because t stands for period, equals, and now here's our slope, 0.046, and then instead of x we have the square root of mass, and instead of b we're going to put the y-intercept, which is actually 0 plus 0, and we can actually just leave that out. Now let's go ahead and use this to make a prediction about what the mass would be for a given period. Actually, let me first mention that this number here, the slope, this sort of represents the number of seconds you get for each gram of additional mass. But let's go ahead and try to use this to make a prediction. So let's figure out the period. So what is the period for a 1,500 gram mass? All right, so let's write down our mathematical model. T equals 0.046 times the square root of, and now let's put the mass in, 1,500. And then if we use our calculator, you can pause the video to do that if you'd like. I get a period of 1.78 seconds. Period of 1.78 seconds. And to show that, let's go back up to our original graph, our non-linearized graph. Let me shrink this and get this out of here. So here's our nonlinear graph. So the advantage to be able to come up with an equation is now we can predict masses that are way beyond the range of the actual graph. Okay, way up here. This 1,500 grams is way out here. And it would be hard to predict how exactly that curves, but once we have an equation, why we can do that. So again, the general process is to take your original data and then to figure out what's the mathematical relationship between that data and the graph. We saw this was a increasing shrinking rate, which is a square root function, and I will tell you what all of the graph functions are. So we took the square root of the mass. Instead of plotting the mass, we plotted the square root of the mass, and we got a nice linear graph. We could then find the equation, and that equation then can work to help us make predictions about, mathematical predictions about the relationship between mass and period. I want to do one more example, and we'll pick that up here and then probably into the next segment. All right, so in my next example, what I want to do is imagine our frog again, and the frog is going to jump from a ledge and fall, and fall down like that. You're going to land safely in the pond. And so what I want to do is make a plot of time falling and of the distance that he's fallen. And if I do that, it turns out that after 1 second, let's say he fell 1 meter, and after 2 seconds he'd have fallen 4 meters, and after 3 seconds he'd have fallen 9 meters, and after 4 seconds 16 meters, and after 5 seconds 25 meters. All right, so let's say that's how far he fell after each one of those points in time. So now we can go ahead and plot a graph, and if we plot that on a graph, we get, let's see, we'll put distance here in meters, put time here in seconds, and what we get if we plot this is a graph like this. All right, so this is an increasing, growing rate. Now, an increasing growing rate graph is also known as a y equals x squared graph. So in the next segment, we'll pick up how to linearize this and how we can use that linear model.